Today we're going to take a look at logarithmic functions. So here's the graph of an exponential function. This is 10 to the x. Notice how our graph is asymptotic here, increases very quickly. It has a domain of all real numbers and a range of only positives. We only go from 0 to infinity. And we've got an intercept here at 0, 1. If we were to talk about the inverse of this function, we know that the inverse would be the reflection of 10 to the x over the line y equals x. So the reflection of that would be over here somewhere on the other side of that line. And on the next slide, we've got a picture of both of those functions. So here we have in blue 10 to the x. In green we've got our y equals x. And then over here in red we've got the inverse of f of x equals 10 to the x. Now the inverse of this function is called y equals log base 10 of x. So this is our logarithmic function. Notice how it's also increasing. Exponential functions increase quickly. Log functions increase but slowly. Our intercept here was 0, 1. Here we've got an intercept at 1, 0. Also notice the domain. We've got a restriction. The domain would be all reals greater than 0, and the range would be all reals. Also notice the way that this is written. Here we've got 10 to the x, 10 is our base. Here, this is log base 10. Now, just like you can have an exponential function with any base, this could be 5 to the x, or 50 to the x, or negative 1,000,000 to the x. Here, with logs, we can have almost any base. We keep this number greater than 0. So this will always be a positive number down here. But base 10 is special, so special that we usually write it just like that, without the base. So if you see a logarithmic expression without a base, you know that it must be base 10. Any other base, it has to be written down. So again, this is called the common logarithm. Here we have another exponential function. Now instead of 10 to the x, we're looking at e to the x. Again, this is increasing quickly, whereas its inverse is increasing slowly. This is another logarithmic function. This is y equals log, but instead of base 10, this is base e. Notice here, the base is e for an exponent. Here the base is e for logarithms. Now this is also a famous logarithm. So we often see this not written as log base e, but as ln of x. So these mean the same things right here. And this has a special name. This is the natural logarithm. So if you were asked to write the inverse of y equals 3 to the x, the inverse must be a log function with a base of 3. So 3 to the x and log base 3 are inverse functions. Now you might remember in chapter 1 we talked about transformations of functions. And here we have a transformation of log base 3 of x. We're adding 1 to x, which means that this will shift the graph 1 unit to the left. And you should see that here, that instead of being asymptotic to the y-axis, this is asymptotic to the line x equals negative 1. So our basic log function was shifted to the left 1 unit. So if you were asked for the domain of this particular function, it would be negative 1 to infinity. Now let's say you don't have the graph in front of you. You can think about this graphically as a shift left 1 unit, or we can just take the expression within the parentheses and set that greater than 0. We get x must be greater than -1, which is exactly what we have written up here above. So in summary, log functions and exponential functions are inverses of each other. The domain of your basic log function would be 0 to infinity. If you had a transformation or translation and you were adding or subtracting something from x, you would set whatever the expression is so that it is greater than 0 and solve. And then you met two different logarithms. You've got the common log, which is base 10, and the natural log, which is base e, and we write that as ln x.